Any questions about yesterday's or lecture or tutorial? Did anyone try to do this problem of finding out what the form of the one-point function of a primary operator that's a distance xd, say, equals d, away from a boundary or an interface that's located at xd equals 0? And this problem is important in statistical mechanics when you want to study the response of a spin in the bulk, meaning away from the boundary, as a function of the choice of boundary conditions or interface that lives here. That's something that hopefully we will get to study systems with such boundaries. So did anyone try to do this? Yes?
Where you replace the distance by d.
Replace the distance by?
Like by the method of image charge or something like that. That's the idea.
Morally, but how will you derive from first principles?
Well, the function has to be, or it has to be covariant under the dilatation, which fixes the origin. So it also fixes the boundary.
No, so the first question that you have to ask is what are the symmetries of this configuration?
Okay, so yeah, so the symmetry is translation along the boundary, which tells us that it can only depend on d.
Okay, so just to maybe flesh it out more slowly. So if you put a system at a boundary at a fixed coordinate xd, you clearly break translational invariance in the x direction. So let's list what are the unbroken symmetries due to the presence of a boundary or interface. This in condensed matter physics sometimes they're called impurity problems because you have something special happening at the word line of some particle. So originally we had, so imagine that this is in RD, and we have coordinates x1 up to xd. So originally we had translation generators from P1 to PD, right? So now what you have to, yes?
With distance
Yes.
and power law will be about delta.
Yes, so now the question is how do you derive that?
Just from physical consideration, it can depend on this coordinate,
Yes.
and it should have a proper dimension.
That's right, yeah. Do people understand that, or do you want me to teach you? I mean, the essential point that you should think about is that of the symmetries that we originally started with, this one is broken. So I cannot impose it. So that means that if I impose translational invariance along all directions which are along the defect, that just means that this function, so invariance under this means that this object cannot be a function of x1 or x2 up to xd minus 1, but it doesn't tell us anything about the fact that it can be a function of xd, the coordinate along which we have broken translational invariance. And now essentially, well, if you want to really understand what's happening, it would be nice for you to identify what are the unbroken Lorentz generators. So it is clear that if you put a defect here, a subset of the original d-dimensional Lorentz group are broken. So maybe write them down. Then it should be clear that some are broken. And you just list down what they are. It should be quite easy. The dilatations are unbroken because if I do dilatation, nothing in the picture changes, right? And then also the special conformal transformations, and that it's either you have an intuition or you can check just explicitly. Also, this guy is broken. So now all that you have to do is impose dilatation covariance, and this indeed gives you that the only function of xd that will scale with the right power of the anomalous dimension is 1 over xd to the delta. Okay. Okay, so now, so yesterday we described the form of the correlation functions of, so yesterday we did the correlation functions of scalar primaries, operators. We saw that all correlation functions are power law. They have power law behavior that is a mathematical representation of the scaling behavior that conformal field theories have. We saw that the 2 and the 3-point function, the position dependence is completely fixed by symmetry, by imposing the fact that the theory is conformal invariant. Then we saw that for the 4-point function, something interesting started happening, that the position dependence is not completely fixed. It's a function of some invariant coordinates, invariant under the conformal transformations. And each correlation function will come with its own function of those coordinates, and we will compute such functions for specific models. We also, I mean, the other thing that was important, of course, is that the behavior of the 2, 3, and 4-point functions are functions of these scaling dimensions, delta. Okay, and therefore we can extract the scaling dimensions of operators by computing, say, the 2-point function of operators in the plane. Okay, and just reading out what the power law behavior is as a function of the distance. So today, what I want to do a little bit of is how to generalize this from scalar operators to tensor operators. The reason this is important is that, as I already said, that in any conformal field theory, there is at the very least 2 operators. You have the identity operator, which is not very interesting. And then we have one that's much more interesting, which is the stress energy tensor, or energy momentum tensor. That is the tensor from which the conserved currents of conformal transformations are constructed. And physically, they measure different quantities. For example, so T00 measures the energy density. T0I measures the momentum density, and so on, okay? And almost by definition, since conformal transformations are generated by the stress tensor, any CFT has to have a stress tensor. In general, of course, these CFTs, apart from having these 2 operators, have many other interesting ones, which are the other primary operators, okay? Also, on top of that, you can have a CFT that, so the first case that we will consider is not the stress tensor. We'll start with something a bit simpler, but which is also relevant. We'll start with the primary operator, which is a vector. Vector, and it's clear what I mean here under the Lorentz group. Okay? An example of that would be if your theory has a global symmetry. It need not be a global symmetry associated to conformal transformation. It could be, say, that you have a flavor symmetry. So you have some transformation that, like in QCD, you have exactly flavor symmetry. Some rotation that acts by a constant phase rotation on all the fields, and it can leave the whole theory invariant. Associated to this, there will be a conserved current. J mu. That satisfies this. So what we want to now do is to use just essentially following almost line by line what I did yesterday for scalars, but now for vector. What is the form of the two-point function of an operator that's a vector, a primary which is a vector? So we want to calculate things like this. So I will just state and convince yourself that the one-point function, if I had looked at the one-point function of an operator that is a vector, that the one-point function will vanish, just as a direct consequence of Lorentz invariant. It has nothing to do with conformal invariance. It's a statement of Lorentz invariance. So the first non-trivial correlator will be the two-point function of the currents. We will not, let me put them down. Doesn't matter. Using this logic, if you are more ambitious, one could try to construct the three-point function. But things, when you have non-scalar operators, become quite complicated. So for the lecture, I'll just do the two-point function of the current and of the stress tensor. But I'll present the tools that if you really wanted, you would be able to compute the two- and three-point function, at least of the current. For the stress tensor, it's quite complicated because there are many different tensor structures that can appear. But at least for the three-point function of the current, you would know how to do it. So what was the logic? We want to, let me try to use consistent notation. So I think I was using this notation yesterday. So we went to study, we want to study this equation. Okay? This is the statement that the two-point function is conformal invariant. Okay? Now, without further ado, I will claim, given our discussion yesterday, that translation, rotation invariance, and dilatation invariance tells us that, so let me write, tells us that this guy is 1 over x1 minus x2 to the 2 delta. So it's a function of the distance. And you have a tensor here. Of course, this guy has two indices here, so you have to construct an object there with two indices. And this is a tensor that will be a function of the distance x1 minus x2. I mean, what property will this tensor have to have in order for this right-hand side to have the right scaling behavior? What will be the scaling weight of alpha have to be? No, so right now I'm just asking as a function of x. How does alpha have to scale if I rescale if I do a dilatation?
It must not scale at all.
Exactly. So it has to have weight 0. So alpha will be a tensor of scaling weight 0. Because I have already counted for the right scaling weight by putting here in the denominator 1 over the distance to delta. So I have the scaling weight of this guy and the scaling weight of that guy. Okay. So now what I have to do is, okay, and in this equation, of course, sorry. So to be consistent, I have to write this, right? So now what I have to do is use that we know how a primary, which is a vector, transforms under conformal transformations, and equate the left-hand side with the right-hand side, okay? Yeah, so let me just write it, and if you want more details, I will write it down. So I have to introduce some tensor. I'm worried that I use I for a slightly different notation, so let me call it J. Don't confuse the J with two indices with the J of the current. Okay, let me write it in 2 steps, because just to be more clear. So if I have J mu x tilde, this is some tensor E mu rho of x times G rho of x. And I guess in this notation I'm using now, they call it J. There will be an x tilde squared to the 2 delta here. Okay. Sorry, the thing I forgot to mention is that now I'm looking at the behavior of the correlator under inversions. Okay, so I'm performing an inversion. So I'm sending x to x tilde, which is x mu over x squared. Okay, and I'm just recalling how a primary operator, which is a vector, transforms under inversion. So if it was a scalar, remember, then we did it for a scalar, we just had that the operator had this Jacobian factor 1 over x tilde to the 2 delta times the operator itself. And now, of course, you have to do a rotation on the spin indices of the operator. So that's why you change. You have to put this rotation matrix in the transformation, where this matrix G mu rho is explicitly G mu rho minus 2 rho x mu divided by x squared. Okay. Is this clear what I did? This guy is nothing but the derivative of x rho with respect to x tilde mu, where x tilde is this inversion. Okay? So using the fact that I know how each of the currents transforms, I get the following equation. So let me erase this a little bit. Let me see if I can fit it here. I get this equation that I mu rho x1, sorry, J, J nu sigma at x2 times 1 over x1 tilde to the delta, 1 over x2 tilde to the delta. So this is just the transformation of each of these two guys, right? Times okay, let me do it. So this guy is this, right? And now this guy is nothing but, I can use that formula, right? So it's alpha rho sigma as a function of x1 minus x2 divided by x12 to the 2 delta. Okay? So put here the alpha tilde. Okay. No, sorry. So I'm making a mess. So here, yes, and this guy has to equal. Okay, now I use this formula that I used many times yesterday and that you derived, which relates the distance of the inverted coordinates with the distance of the original coordinates. That, what ends up doing is essentially getting rid of this. Yes? So then I'm left with the following equation for alpha. So conformal invariance tells us that this matrix alpha, which is undetermined, has to satisfy the following equation. So I'll write it as a metric equation. So as a okay, all that I did is to combine the two j's with alpha and equate it to the right-hand side. And now what I'll claim is that the solution to this equation is actually to take alpha mu nu x1 minus x2 to be precisely this tensor. And we will check. So this will have to be j mu nu of x1 minus x2. Okay. And the reason that this is true is that this follows from the following identity. Which is the statement that alpha mu nu j mu nu at inverted points is transforms by conjugation with this matrix itself. So j mu rho of x1, j rho sigma of x1 minus x2, and j sigma nu x2. Okay, so I'm not proving this to you, but I think you would know how to prove it. We know explicitly what j mu nu is as a function of the coordinates. So you have to now compute j mu nu as a function of the inverted coordinates and write it in terms of this way. Geometrically, this statement, and if you don't understand, don't worry about it, is the statement that j transforms like a connection. So j at two different points goes back to j, but you have to rotate the initial point and the final point. Okay? So I don't know if you've seen connections in general relativity or gauge theories, but if you don't know that, don't worry about it. This just follows from a direct calculation. So from this, we conclude that the two-point function of a conserved curve of a vector, a primary vector, is precisely this where j is that thing I wrote there. Is that clear? Yes.
Can I ask a couple of questions? One, is it clear why a conserved current is a primary operator?
In general, it's not. Like, well, the stress tensor, as we will see, the stress tensor in two dimensions is not a primary, it's a center. So, no, so I'm just saying, I just gave you an example of something that could be a vector.
Okay. So if it is a primary.
It is a, yeah, so this only works if it's a primary. And we will find an important, in 2 dimensions, for example, something that's very different than in higher dimensions is that one of the currents, which is the stress tensor, is actually a descendant.
Okay. And my other question is there an easy way to see why J mu would transform like this under inversions out of the formula we were given? I mean, we were writing the transformation of general primary operators, and it had this LAD, this matrix of R. Is there an easy way to see why this becomes? I mean, this looks very nice intuitively because it's just like the usual vector transformation,
yes,
along with the scaling dimension. But
yes. Well,
is
this,
it easy
this,
to
is the
derive
this is the statement that for a vector, the representation that our matrix is precisely this.
So it is easy. Yes, that's the R matrix, but then the representation on the I mean, when we were writing the rule for transforming fields, we had the representation of the R matrix.
Yes, but this is the okay. So maybe write it more explicitly. So if I have a current, which is a vector, explicitly. It transforms like a tensor to transform in general relativity. Just that x tilde is a specific form of information. That's all I use. So this J matrix is this Jacobian of the transformation. And this is just a specific form of the representation of the Lorentz group for a vector. That's all. Any other question or clarification?
John, when you
Yes.
say it transforms like a connection, you mean like the holonomy of the connection?
Well, what I mean is that you have parallel transport of something between x
Okay,
and y.
yes, like the holonomy.
Holonomy. Yeah, so if this word is unfamiliar, don't worry about it. You will learn it eventually. What is the other?
Can I have a question? This global symmetry, can you also make something for local symmetry?
Local symmetries are not symmetries. That's global.
They are not symmetries under conformal transformation, right?
Sorry. No, I'm just saying that a gauge symmetry
Yeah.
is not really symmetry. That's a problem that many textbooks have. They call it a gauge symmetry, but it's not a symmetry. Because the states, so the Hilbert space of your theory has to be singlets, invariant under gauge transformation. So it's a redundancy. So it's a way of writing the theory in a more redundant way to make things manifest, like unitarity, Lorentz invariant, and so on. But your states are not in representation of the gauge symmetry. They're singlets. The only things that are real symmetries are the global ones. But so this I called it. I just wanted to give you an example of something that has a vector index that you have heard about before, which is a conserved current. But it need not be a conserved current; it could be something else. I mean. Okay, so this was for the for a vector primary operator. Now what I want to do is to do it for the stress tensor. And then I'll quit with that because as you see, as you start going away from scalars, you have to throw around more and more indices, and it's not fun for me to write, and it's not fun for you to see. So it's not. But I think I hope, I mean, is the logic at least completely clear of how to do it? I mean, the details of the calculation might be a bit, you have to do it, but is the logic clear that what you have to do is impose as much constraints as possible, and then just ensure that impose the condition, solve the condition that the correlation function is invariant under the transformation. That's it. Yes. Yes, here I was a bit sloppy because I factored out this factor of 1 over x to the square. Is that what you were doing?
Yeah.
Yes.
So it's taken to be.
Yeah, so that's why. So I think in the lecture, in some previous tutorial, I called the whole thing. So this guy with 1 over x tilde square, we called it I. So here, strictly speaking, I have to multiply. You're right.
But from now on, when you refer to that for inversions, you're meaning the factor.
No, so when I call j, I just forget about the right hand side. I just mean this,
Okay.
which is that. I think we called I with the x tilde square, right? Yeah. Okay. So I just realized I was writing that I called I to something. We already called I something else. Okay. So now let's do quickly the stress energy tensor. Essentially, the logic is that once you have this basic object, this J mu nu, you can construct the tensor structure for operators that are in other representations just by putting together this basic object. This is like the way that, how do you construct tensor representations? Well, you construct them by multiplying together the vector representation and symmetrizing or anti-symmetrizing accordingly to the properties of the tensor. So here is the same. We know the transformation properties, the transformation matrix for the vector. So by putting this guy together, we can construct the representation matrix for any tensor. So that's the strategy we will use. So now I want to look at the two-point function of the stress tensor. So now the number of indices are growing exponentially, fortunately. But soon we'll go to 2 dimensions where there are no indices. That's good. You'll see why. So again, I claim that just based on scale using rotational invariance, translational invariance, and scale invariance, this is the general form of the 2-point function. Here I use D because the stress tensor always has dimension D. And one way to see that is that we know that just from the algebra that the translation generator has scaling dimension 1, right? And you know that you construct P mu by integrating over the special coordinates the 0th component of the stress tensor. So if this guy has a scaling weight 1, this guy has a scaling weight minus D minus 1, then this guy has to have a scaling weight D. So the stress tensor always has a scaling dimension D. Yes?
Does it always have scaling dimension D even if you consider loop corrections and so on?
Well, so these are already for the conformal field theory. So I am at the fixed point. Okay. But the fixed point is definitely. Now, you may worry about if you're not at the fixed point. I think a priori then, yes, like anything else, you will acquire a normal dimension. Okay. So then all that we have to impose now is that this guy has the symmetry properties of this guy on the left-hand side. So it has to be symmetric traceless in mu nu and rho sigma. So and the way we will construct it using this intuition that if we know how a vector transforms, we know how a tensor transforms by just taking the tensor product. I will just write down the answer and then we'll discuss it. So we will construct this tensor from this basic object that we constructed here, this J, this connection. So it's going to be 1/2 J mu rho X, J nu sigma at Y. Oh, sorry, at X. Okay, so here I'm just calling it just at the point, doesn't matter, right? So now I have to symmetrize. So since the stress tensor is symmetric in mu nu and rho sigma, I have to symmetrize the first term that couples mu rho with nu sigma. I have to symmetrize with respect to flipping nu with mu and rho with sigma, but that just means that I have to write here J nu rho at X, J mu sigma at X. So this guy already has the nice property that it is symmetric. It has the symmetry properties of each of the two stress tensors. But now we have to use that in a conformal field theory. We will be working in the frame where the stress tensor is traceless. And this guy in the right-hand side is not traceless. It's not traceless if I contract this, object with eta mu nu. This guy should be 0 because the stress tensor is traceless. It should also be traceless if I contract this side with eta rho sigma. But this is not. So what you have to do is remove the trace here, which is 1/d delta mu nu delta rho sigma. Okay. And now you can verify that this guy is indeed symmetric traceless. Okay.
The half in front of the delta sigma.
No. No. The half is okay. So. Okay. And as we will see, at least in 2 dimensions, maybe also in higher dimensions if we have time, this object will be a very important observable in conformal field theories. This is something that I also briefly mentioned earlier in the lecture and has the name of a central charge. Okay. And provides some of the key properties, or kind of the simplest, it gives us information about one of the simplest labels of a conformal field theory. Each conformal field theory, if 2 conformal field theories have a different central charge, okay, if 2 CFTs have a different central charge, they cannot be equivalent. So one way of characterizing CFTs is by specifying what the value of the central charge of that CFT is. And for example, if you want to, say in higher dimensions, if you want to do it, so we know that free field theories are kind of the simplest example of CFTs. So if, just to give you an example that these numbers are something very concrete, if you computed in 4 dimensions the central charge for a theory that has NS scalar fields, NV vectors, and NF fermions, you get some, okay, so one geometrical factor, 1/π⁴, NS plus 2NF plus 4NV. And the way you would compute it is that you write down the stress energy tensor associated, and I think you've in the homework, you are computing the stress energy tensor for scalars and vectors. So just write down the stress energy tensor for a scalar, a vector, and a fermion. Forget about the fermion if that's too complicated. And just calculate in free field theory the 2-point function of this object. So this T mu nu is a composite operator, right? Roughly speaking, for a scalar, forgetting all the indices, just to give you a flavor how you would compute it, you're computing the 2-point function of a composite operator at X and Y. The stress tensor is quadratic in the fields. We'll have 2 phi's, right? because the theory is free, that's all you have, always 2 phi's. So what you would have to do is compute the contraction of d phi square at x. There are, of course, more terms, right? Because the stress tensor has a piece that has d mu, d phi, d nu, d phi, and then eta, one with eta. But just, so you have to do some combinatorics. And then you contract this with d phi squared at y. And by doing this carefully, you should get these numbers. Okay. Yes.
Of this quantity which characterizes your conformity.
Yeah, so this had to do with the discussion that was probably a bit opaque, because this has to do with the fact that I said that if you're, so we're here we're in flat space.
Yeah.
But if you're in a curved space, you have this notion of a conformal anomaly that I discussed. And this was a statement that the trace of the stress tensor, if you couple your CFT to a curved background, is actually not 0 anymore. That means that in the curved background, the scaling symmetry is broken, conformal symmetry is broken. And the thing that ends up happening, and I'm not showing you how to go from here to here. I may do it into the. I will do it in 2 dimensions. How to go from this anomaly, which is a 1-point function of the stress tensor, to the 2-point function in flat space. What one can show is that if you couple the theory to a curved background, the right-hand side is non-zero, but it is essentially fixed by some basic requirements like dimensional analysis, and you get tensors, geometrical objects that have information about what curved manifold you put the theory on. So remember that I said that in 4 dimensions, let's do it in 2 dimensions, which is a bit simpler. In 2 dimensions, the only object that you can construct here for the right-hand side is an object that was something like minus ct over 12 times the Ricci scalar of the metric that you couple the theory to. So geometrically, this ct, well, it appears here, but more fundamentally appears from is the measure of by how much you've broken conformal symmetry when you couple the theory to a curved background.
Cohomology at this step, or is there something else?
Well, in 2 dimensions, we will see that yes. So this guy has to do, this same number will appear, but okay, I'm getting ahead of my time, so this will not make much sense. We'll come back to it. This number will appear as a central, so we'll have a conformal algebra in 2 dimensions that they will have a commutation relation, classically, but then quantum mechanically we'll see that there is a correction to the commutation relation that are exactly proportional to this shift. And this will be a central extension. You can think of central extension in terms of Lie algebra cohomology, but I don't think this is the place to discuss it. So definitely this has interpretation in terms of cohomology if you want to, or in terms of extending the conformal algebra by one or more element. But this is only true in 2 dimensions, which is actually what we're going to discuss next. Okay. Any more questions? Yes?
Is the stress tensor energy a primary tensor?
In higher dimensions, yes. In 2 dimensions, no. We'll see that in 2 dimensions, the stress tensor is a descendant of the identity. It sounds bizarre, but it's true. And we will see why. That's a good question, because a priori, yeah, it could have not been. So I think I'll quit here. I could, in principle, write down the form of the 3-point function, introducing. So here I introduced this tensor J, which is something that transforms nicely when it acts on 2 points, like x1 and x2. It turns out that there is another nice, depending on your taste, but there is a nice invariant object or transforms covariantly under conformal transformations. You can define a vector that depends on 3 points that transform nicely. Nicely means that in some nice geometrical way like that, like a connection. And then putting together the J's and that guy, you can construct everything. And maybe we will put that in a tutorial, I don't know. but Anna will hate me for this. But maybe not. I mean, these are maybe a little bit more advanced that we want to get. But I'm saying that in principle, what you have to do, once you have the construction of these invariant given 2 points, or covariant tensor given 2 points, and this covariant tensor given 3 points, you can put this together to construct any covariant object, essentially. Okay? So if you really wanted, you could construct, say, the 3-point function of two scalar primaries with a vector primary and so on. But I'm not going to do this, because I want to move to 2 dimensions quickly. But maybe before going to 2 dimensions, let me just very briefly mention a few examples, which some of them we've already discussed, of CFTs in higher dimensions. By higher dimensions, I mean d bigger than 2. We will see that in d equals 2. In some sense, that's the home of conformal field theories for the reasons that I explained in the first 2 lectures and that I will remind you a bit later. The first examples that we had are the free field theories. Any free field theory that you can write down, a free boson, a free scalar, a free Maxwell, or a free fermion is a conformal field theory. Then we constructed what we called non-trivial CFTs. I remind you of this construction of Wilson-Fisher, whose basic idea was to, starting from a free field theory, by going away from 4 dimensions, we made one of the classically marginal coupling, lambda phi to the 4, we made it slightly relevant. And then essentially what we did was to find a solution to the scale invariance equation, which remember was that the fact that if there was a solution to a 0 of the beta function, that signaled that the theory was conformal invariant. A scale, in that case, a scale invariant, but then you can, on top of that, show that it's conformal invariant. And in this case, we saw that if you go to 4 minus epsilon dimensions, this guy becomes slightly relevant, so it flows away from this fixed point, and then eventually hits this other fixed point, which is the Wilson-Fisher fixed point. Okay? And the way we did that was to calculate beta lambda. It had a classical piece due to this funny business of going slightly below 4 dimensions, so as to give a lambda a positive mass dimension. And then we compensated that with the 1 loop, so I don't remember the number, so some number B0 lambda square. So this was the 1 loop contribution to the beta function. And then what we did is just to find a 0 here. So we found a 0 at lambda proportional. Okay, so lambda star was epsilon over B0. Okay. And by making epsilon sufficiently small, we were still moving in the lambda axis to a nearby point where you could still use perturbation theory. Because the value of the coupling lambda star, is still small at the fixed point. You can still calculate reliably correlators here using perturbation theory. Okay. And in a way, this was the first example of CFT that was constructed in the 70s. And as I said, this is how people back then computed critical exponents for magnets and water and all kinds of things in 3 dimensions by doing analytically continuing all the results to epsilon equals 1 and resumming the series. The other more modern construction of non-trivial CFTs, but that has exactly the same logic. The logic is that, except for supersymmetric theories that I'm going to briefly describe next, the beta function of any theory is non-zero quantum mechanically. So one way you can try to fish for a fixed point that's perturbative, again, which that means that the value of the coupling at the fixed point is sufficiently small that you can still calculate using standard rules of perturbation theory, is to cancel the first term of the beta function with the second term. So in the case of Wilson-Fisher, we canceled a classical term or 3-level term with a 1-loop term. Then there was a trick noticed by Banks and Zaks. This is in the context of gauge theories. Where there, if you remember, so if you study the gauge theories, classically the beta function is 0, but you have a 1-loop contribution, which has an important minus sign, okay? That's the statement that gauge theories, unless you add too much matter, they're asymptotically free. They are very quickly coupled. They're perturbative in the high energy regime, and they are non-perturbative, very strongly coupled in the infrared. So you get something like V0 cubed, so that would be the 1-loop contribution. And then you get a hard to compute, but computable 2-loop contribution. And this B0 and B1 are explicit functions of the matter content of the gauge theory. So it knows about the number of colors, it knows about the number of fermions, transforming some representation of the gauge group. It knows about the number of scalars that transform in some other representation of the gauge group. And what they notice is that there are special circumstances. So first of all, that V0 is positive and so actually both B0 and B1 are positive, having already pulled the sign here. Then what you can find by looking at the explicit form of B0 and B1 as a function of the matter field, the choice of matter that you have, there exist solutions to this equation where you kill the 1-loop term with the 2-loop term, such that what essentially you get by just solving this is B0 equals B1, such that this is still much smaller than 1, okay? So the logic is a bit similar to that. You stay in 4 dimensions, but you compensate the leading 1-loop term with a 2-loop term. You find a non-trivial fixed point, and then you can calculate in perturbation theory there. Okay, and there are quite a few examples of such theories, and they're also quite useful. And just because time, I mean, there are many other constructions I could give you. The place where there are many conformal field theories is if you make the theory supersymmetric. So that's something that I think you will see later in the year if you're interested in those subjects. And the reason that, just to give you an intuition of why is it more natural to get simple fixed points in higher dimensions, is that when you have supersymmetry, you need both bosons and fermions in the theory. And quantum corrections induced by bosons and fermions, in some sense, come with opposite signs. So if the theory has a finely tuned spectrum of bosonic particles and fermionic particles, the quantum corrections induced by bosons are exactly canceled by fermions. And therefore, you can construct theories that have a 0 beta function, okay? And in fact, there's an infinite number of supersymmetric conformal field theories in 4 dimensions. And this has been a subject of great activity in the last 10 or 15 years. They're both studied from the point of view of gauge theory or field theory, but also from the point of view of the ADS-50 correspondence, because many of these supersymmetric conformal field theories have a dual description in terms of some ADS geometry. And this, I believe, you will also learn later in the course. Well, if you take that course, of course. Okay, so at this point, I may come back later to make comments in higher dimensions, but at this point, I will stop the general discussion in higher dimensions and we'll go down to 2 dimensions. So it is a good time to ask any question about CFTs in higher dimensions. So one could go much more deeply on any of these points, but I think it will be the simplest and most, and we will have a lot of interesting applications by just going to 2 dimensions. So everything is clear? But is either maximally clear or maximally unclear? That's silence. Okay, so let's start with 2 dimensions. Sorry?
The 2 dimensions for the rest of the lecture?
No, we want to do everything for the rest of the lecture, but time is fine. But so I have to make some choices. Either yeah. So in practice, for the rest of the lecture, will be mostly in 2 dimensions. But when there are insights that I can provide in higher dimensions, I will make parenthetical comments that are hopefully useful. The thing that's nice about 2 dimensions as opposed to higher dimensions is that in order to construct, it's not so easy unless you have supersymmetry to construct tractable example of CFTs in higher dimensions. But that's exactly the opposite in 2 dimensions. 2 dimensions, conformal filters are incredibly tractable. There are many, many, many examples, and we'll be able to extract lessons from that. But you want to take a particular example of a CFT here and study it in detail. And I think you will do that, well, when you study any course for supersymmetry. That's kind of the best understood example of a CFT and the simplest example of a CFT in 4 dimensions. The reason I also wanted to go to 2 dimensions is that, okay, so. Is that these guys have a very, so 2-dimensional CFTs is an incredibly rich and beautiful subject and has many, many applications to many areas of both physics and mathematics. But 2 of the direct applications that it has that makes them interesting just by themselves is that they describe, remember that there were 2 main applications of 2-dimensional CFTs. One was to classical critical phenomena in 2 dimensions. So the behavior of phase transition, second order or higher phase transitions in 2 dimensions. It describes the critical points in the phase diagram of magnets and water and very many types of models in 2 dimensions. It also describes quantum critical points in 1 dimension. So here the prototypical example that we'll have in mind is the 2-dimensionalizing model, which I briefly described. I can describe it again if people want, but we'll come back to that later in the course anyway. And then the other prototypical example of this kind of connection of CFTs with quantum mechanical spin chains was the antiferromagnetic Heisenberg spin chain. Okay, so these are 2. Actually, there are 3 classical motivations for this. The other one is that this describes the dynamics of string theory. So if you take the course on string theory, you will see that the dynamics of the string and the dynamics of space-time follow from imposing that the theory that lives on the worldsheet is conformal field theory. Okay, so the way we understand string theory in the perturbative description is in terms of in the language of exactly two-dimensional conformal field theories. So if you take that course, you will see in more detail how conformal field theories arise in the study of string theory. Okay, good. So already in the first lecture, I gave you some motivation why, a very kinematical motivation of why there are many CFTs in 2 dimensions. And the reason arose that from this kind of picture, that one way of getting to new fixed points is by starting with a free field theory and perturbing by a relevant operator. Okay? Remember that when we listed the relevant operators, say in a scalar field theory, in 4 and 6 dimensions, the number of relevant operators was very, very small. They were essentially a handful. But in 2 dimensions, essentially any polynomial of the field is a relevant operator. So then you expect that if you flow in an arbitrary number of directions, you may be able to hit a fixed point because there are many repulsive directions away from the free field point. So just like I was moving in this direction here by tuning this lambda phi to the 4, essentially by tuning in any direction, I may be able to find a fixed point somewhere else in 2 dimensions because all these different directions are relevant, okay? But that's just to give you some intuition of why they're ubiquitous in 2 dimensions. But before getting there, let's quickly go through what's new. And there are some important new things. I lost I don't like this eraser. I can make a mess. Okay. So now what we want to do is first study. We briefly already said that in one of the lectures about what's special about conformal transformations in 2 dimensions. So let me remind you what those are. But since we've done a lot of the discussion in arbitrary dimensions, some of the things will be just slight generalizations of things that we've already done. So it should be hopefully quite clear what's happening. So of course, now we're going to be in 2 dimensions. And if we're in Euclidean signature, it will be very convenient, as you will see, to use complex coordinates. So we can use the power of complex analysis. So we will combine our coordinates x1 and x2 into complex coordinates, x1 plus x2, and z bar x1 minus x2. We will define then the derivatives operator. So this will be this. Is it clear why that sign there is minus? No?
Well, if you take derivative of z, you will get 1.
Yes.
If you then have the minus, then you will get
yes. Yes. So the way to see that is that if you differentiate z, you get 1. If you differentiate z bar, you get 0. Yeah, that's the truth. It wasn't a trick question, really. It was just to make sure that you're awake. Okay. So now I want to study the. Let's consider first the infinitesimal transformation. But so first, let me do it in real coordinates, just to remind you what the formula for the transformations that generate infinitesimal conformal transformations. We had this equation, remember? So the mu V mu. So we make x mu goes into x mu plus v mu. So in general here we had the factor of 2 over d that we derived by expanding the conformal Killing equation on the left and on the right. So now something what's special about what happens in 2 dimensions is that in d equals 2, this is just 1. Okay. So this elementary fact will have far-reaching consequences. Because, and this I think I already wrote in one of the lectures, if we now study this equation in 2 dimensions by, say, choosing all possible values of mu and nu, you get 2 independent equations. You get that A1 V1 equals D2 V2, and which one do I want to choose? And then D1 V2 equals minus D2 V1, right? So the first equation is just obtained by setting mu nu equals 1, and noting that the right-hand side cancels. So here I get twice d nu 1 v1. On the right-hand side, I get one term that is d1 v1. So that cancels the 2 on the left-hand side. And then I equate what's on the left-hand side, which is one copy of d1 v1, with whatever is left in the divergence here, which is d2 v2. Okay. And this one just follows by setting mu to 1 and v to 2. The right-hand side is 0, right? Delta mu nu is 0. So all that I have is that d1 v2 plus d2 v1 equals 0. Otherwise, written like this. Okay. And as we already mentioned, these equations are the Cauchy-Riemann equations that you may have, that you probably have seen in before. And to really characterize what the conformal transformations are, it is convenient to use these complex coordinates and define V as V1 plus IV2. Then we have Z, as I defined here. Then these 2 equations are equivalent to the statement that the antiholomorphic derivative of V has to vanish. Okay? So this tells us, so this implies that the infinitesimal conformal transformations are holomorphic maps. So this is exactly what the definition of a holomorphic map is. It's a map whose antiholomorphic derivative vanishes. Okay. Very good. Is this clear? Okay. Notice another way of seeing it in the finite transformation is that if I directly look at the metric in complex coordinates, so this was the infinitesimal analysis. But if you write just the flat metric in terms of complex coordinates, you agree that the metric just looks at d times dz bar, right? You have, this is the same as dx1 squared plus dx2 squared. So if now I make a holomorphic transformation, so I map z to omega z, the holomorphic map, so omega is a function of z, not of z bar. Then this guy, just using the chain rule, is the same as dw dz squared. Am I making a mess? No, I think I'm. Yeah, so now let me write it this way. It depends where you write the Jacobian, to the right or to the left. So if I write it like this, I have to put it to the left. So you see that if you make a holomorphic change of coordinates, then the metric preserves exactly the form, right? Up to a scale factor. So the conformal factor is this derivative. Okay? So here we can see quite explicitly that indeed holomorphic map is a conformal transformation in 2 dimensions because it just rescales the metric by some factor. So now let's parameterize the infinitesimal transformations. So just like in higher dimensions, remember that conformal transformations were arbitrary vector fields which were at most quadratic in the coordinates. Now the vector field can have an arbitrary power. So we can find a basis where this is just, so if I write it like this, because sometimes I call it G tilde, sometimes I call it W, hope it's not too confusing. Then BZ has an arbitrary Laurent expansion. Okay, so it has an arbitrary expansion in powers of Z, essentially. It can have poles. It can also have arbitrary polynomials of Z. Okay. This is the most general way of parameterizing locally holomorphic map near the origin, that's single valued. And just like in the case of higher dimensions, we associated to each independent vector field from which we constructed the transformation, we associated well, a vector. So to each infinitesimal transformation, we associated a vector field. We can do exactly the same thing here. So for each independent term in the Laurent series, there is an associated vector field. So let's write it down. That tells us how to go from Z to Z plus BZ. If the transformation is small, this is parameterized by a vector that moves you slightly in the tangent space. Fields. So we'll use this notation Ln, which is going to be minus Zn plus 1 Z. This will be for the holomorphic transformations. And then I have an associated one for the Z bars. Okay. So it's clear that Ln, if I let Ln act on a coordinate Z, it maps this to, okay, with some sign that I'm not being careful about. Okay. So it exactly shifts the original coordinate by Zn plus 1. Okay. And now we can, like in the case of higher dimensions, when we constructed the vector fields associated to translations, special conformal transformations, and blah, 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 we were able to derive the algebra, the conformal algebra, by just taking the commutator of the vector fields. Yes?
Why are we allowing
Because locally near the origin, this is allowed, and we will see that allowing singularities in our transformations will be, in fact, incredibly useful. We will very soon see that there are only very special transformations. Only a subset of these transformations are non-singular in the complex plane, more precisely on the Riemann sphere. But we will allow arbitrary transformations that will have a singularity somewhere, and we will extract lots of physics from the behavior of the theory under such singular, quote-unquote singular conformal transformation. Any more questions? So from these two definitions, you can obtain, you take the commutator of these two vector fields, you get n minus m ln plus m. Is that clear how to get this? Okay, let's stare it for a second. If it's not clear, I can do it more deeper. I guess that means it's clear. Not, someone will complain. Then, since the second guy is just the complex conjugate of the other one, this guy will give us the same. And these two guys commute. Okay. So essentially, what we get is the direct sum of this algebra of transformations, which is called the DeWitt algebra. Sometimes it's called the DeWitt algebra. But it's just the algebra of infinitesimal vector fields, holomorphic vector fields. Okay? And the direct sum, because we have one copy for the holomorphic sector, for the z's, and one for the anti-holomorphic sector, the z bars. So something that is very commonly done in CFT is that you can focus most of your attention to one sector, say the holomorphic sector, and the anti-holomorphic sector in some sense just comes along for the right, okay? Also something that you might see commonly done is that it is sometimes convenient to complexify coordinates, so that to treat z and z bar as two independent complex coordinates. So z bar is not z star. And then at the end, if you want to compute some observable, you impose that z bar is z star. But for a lot of the analysis, you can analytically continue things in such a way that z and z bar are two independent complex coordinates. Okay, so now what we want to study more carefully is what are the quote-unquote nice set of conformal transformations. As someone mentioned already, we will see quite soon that not all of them are well behaved throughout the complex plane. So we want to understand which ones are well defined in the complex plane. So something that we overlooked a little bit in the discussion of conformal transformations in higher dimensions, not because I was trying to hide anything, but just to make the discussion not more complicated than it is the fact that there's one subtlety about conformal transformations that you should all, or at least not all, but at least some of you should have common complaint or at least notice that conformal transformation does something very strange in general. It takes an arbitrary point here. You can take it all the way to infinity, right? Like if you do an inversion around the origin, it maps the origin, which is an ordinary point, because all points in Minkowski space are equally good or bad. So there are transformations that map the origin to infinity, okay? So in order to really have the proper action of the conformal group on spacetime, what you have to really do formally is you have to compactify your spacetime. Essentially, you have to add the point at infinity. So that means that you have your plane, but since any point in the plane can be mapped to infinity, what you have to do is add this extra point at infinity. In the case of Euclidean signature, what this does is essentially so add point at infinity. Essentially, what this does is give you the d-dimensional sphere, right? Is this clear, that if you add a point to the plane, that you get the sphere? Geometrically, it should be quite clear. And there is an explicit construction of this using the stereographic projection. So let me do it just for in 2 dimensions. So what I want to do is add the complex plane plus a point at infinity. This gives a two-sphere, sometimes known as the Riemann sphere. And on the Riemann sphere, conformal transformations act nicely because all points, there is no difference between infinity and the rest of the points in the sphere. I mean, infinity, as we will see in a second, is just the north pole of the sphere. So the north pole and the south pole are equally good or bad. So let me just remind you very quickly how this goes. So the stereographic projection, to give you some intuition of what does it mean to add a point at infinity. You may have seen this, I don't know. If you have seen it, let me know, and I will not waste time with this. Sorry? Okay, so I shouldn't explain it then. So all that I want to say is that projecting this onto the plane gives you the complex plane for any point outside the North Pole. And then the North Pole is an extra point that maps to infinity. And that's why geometrically the Riemann sphere is really compactifying the plane by adding a point. Okay? So now what we want to do, forget about that then. Good. And I'll just finish with the analysis of what are the global conformal transformations on the plane. So we want to study what are the vector fields. Okay? So the places we have to worry about by looking at the form of the vector field, where do we have to worry about these guys going badly? We have to worry them going badly at the origin and at infinity, right? So let's first analyze behavior near the origin at z equals 0. So we have that ln, the vector field is ln zn plus 1 ddz. So this guy doesn't have any singularity if n plus 1 is non-negative, right? Which means that n has to be bigger or equal than -1. And now we want to, the other dangerous place is the behavior near infinity. And the way we study the behavior of the vector field near infinity is that we go to the coordinate patch that's suitable up there. So we define the coordinate w, which is 1 over z, and write the vector field in terms of the suitable coordinates near the North Pole. So here, just using this mapping, you get this is minus w to the minus n plus 1. And now we have to compute d dz. So this is dw dz times dw, right? And now I use the fact that w dz is minus 1 over z squared, or equivalently minus omega squared. So this omega square changes the sign of this minus 1 to, okay, maybe you cannot see. So to get minus w 1 minus n, right? So this, you have minus 1 from here, you have plus 2 from here, so you get this. So now sorry? Why do we have 2 minus n's? Yes, you have this, and then I have the. Oh, sorry. Oh, so they were talking about this sign. Sorry. Yes. Okay. Yes, I agree. So now, in order to determine the behavior near infinity, we have to see when this vector field is well behaved. Now, in these coordinates, is at w equals 0. So this guy is well behaved for 1 minus n being non-negative. Otherwise, you can write this as n smaller or equal than 1. I didn't make a mess. That's right. So by analyzing this way, we find that there are only 3 possible globally defined vector fields, holomorphic vector fields. And this will be our friends that you already know from our studies of higher dimensions. So the nice vector fields will be, so n, so will be ln for n between 1 and minus 1, right? One inequality comes from near the origin, the other one comes from near infinity. So let's write them down explicitly. You get L minus 1. So remember that we defined Ln in this way. So you get minus ddz. Also, sometimes I'll use this notation not to, hopefully that's clear. So you get just this. Okay, so what is this transformation? So you get the translation. Then we get L0, which is minus z dz. What is that? The dilatation. And then I have L1, which is minus z squared d. Which one is that? Conformal. So not surprisingly, perhaps, the ones that are globally defined are exactly the ones that are generic in higher dimensions. Okay? So these are the vector fields that are, again, just quadratic on the coordinates. They're 0th order, 1st order, and 2nd order. Okay? And of course, so let me write down the transformations, the infinitesimal and the finite. So the infinitesimal one we already saw, right? It was z goes to z plus epsilon. The dilatation goes to z plus epsilon z. And this guy was z plus epsilon z squared. It is clear how to make finite these two transformations, right? Well, by now you should know also how to make finite this transformation by using this trick of inversion. So can someone tell me what the inversion transformation is in the complex plane? Remember that I said that there is a inversion is a transformation that is discrete and changes orientation. It exists in any dimension, in particular in 2 dimensions. So what's the conformal map associated to inversion?
Z goes to 1 over Z bar.
That's right. So maybe can you explain why?
Because so if we imagine we take a complex number that equals r times e to the I theta, so we made a polar representation. Then if we take z goes to 1 over z, that's like r goes to 1 over r, but also we take the opposite argument.
Yes.
So if we want to end up on the same argument, we need to take the complex conjugate.
That's right. Okay. Yes. So by using, so let me just write it down first here. So here, and if you wish, by doing, so this you can attend by doing inversion, translation, and inversion. We're now inversion, and everyone sit down and convince yourself that why this is an inversion and why it changes orientation. You will find that the integrated form of the infinitesimal special conformal transformation is this. Okay. Looks like that. There is a very convenient way of packaging these three independent transformations into a matrix. So here there are three independent parameters, but you can define these in terms of, these are sometimes called, so the globally defined transformations are called sometimes projective transformations, Mobius transformations. I'm sure there are other names that I'm forgetting. So if you see those names, they're just talking about these globally defined transformations on the sphere. They can be nicely packaged into a transformation like that. That's a projective transformation. So Z goes to the ratio of two linear functions where A, B, C, D are complex numbers that satisfy the constraint with the constraint. No, notice that here I had three parameters, right? So at the end of the day, I have to have three parameters with the constraint that A, D minus the B, C. So if I write A, B, C, D as a matrix, this is the statement that the determinant of this matrix equals 1, okay? So I go from the 4 parameters to 1 parameters. And the reason that this is useful is that composition of conformal transformations, the global ones, is realized as matrix multiplication. So if I make one transformation with parameters A1, A1 to D1 and A2 to D2, you will get the same transformation as M3 multiplying M1 by M2 and plugging in the corresponding numbers here, okay? So just matrix multiplication. Okay. I guess I'm going way over time, so I should probably stop. Let me just say that given that these are the finite forms of the transformations, you can convince yourself now easily that the matrix associated to the three generators is 1 alpha 0 1. That's translations. Dilatations is root lambda 0 0 minus root lambda, and then L1 will be 1 0 minus beta 1. Okay? And all other transformations can be obtained just by concatenating these transformations. Let me just mention that the set of matrices, 2 by 2 matrices that have complex entries and have determinant 1 form a group. Does someone know what the name is? Sorry? I was looking for that. Yeah, that's also used, but it's just SL to C. These are matrices, 2 by 2 matrices with complex entries, and this funny LS is just a statement that it has determinant 1. So what we've concluded in this analysis is that the set of global transformations is equivalent to the SL2C matrices up to some subtlety. Notice that if M is a matrix in SL2C, can people see? Maybe you cannot see here. Do not complain. So if M is an element of SL2C, and this generates a particular conformal transformation given by this, notice that minus M is a different matrix in SL2C, but it generates exactly the same transformation, conformal transformation, because if I reverse the sign of all the entries in the matrix, A, B, C, D, I get exactly the same transformation on the right-hand side for M and minus M. So that's the statement that the set of global conformal transformations is given by SL2C, the set of 2 by 2 matrices with matrix determinant modded out by Z2. And that's just a statement that you have to, you don't have to, but that both M and minus M generate the same conformal transformation, and you have to eliminate the image under Z2 of the SL2C matrix. Yes. Yes, yes. So here I already, I normalized the determinant. I mean, I fixed some particular determinant. Yes. Okay, so let's stop here, and I'll continue tomorrow with 2 dimensions.